All right, we have here that ribbon, the cinnamon roll, and then we unroll it and make it into this. And we do that by first looking at these dots. So let's say this is another ribbon, and we're going to imagine a sphere around each dot of a certain size. And again, the size of that sphere is just one of those parameters. And then you connect them based on, are they within a certain sphere of influence? And maybe you start off with really small spheres, and everybody that's connected has a very strong strength, strong connection. And then you make those spheres bigger, and it makes new connections, but those connections are a little weaker because they're further away. And you keep doing that and doing that. And one way to do that is the weaker connections actually have a higher number associated with them, a higher maybe cost or traversal, you could say. Then for any two given dots within our network, we can say their distance is the number of steps in the path to get from one to the other. And this distance seems much longer than the Euclidean distance would be. You can think about it as, have any of you guys, I want to see a quick for showing of hands, have any of you guys lived in a city that is not planned like a grid? There's parts of Spokane that are kind of like a grid, but there are big cities like Boston, where I'm from, that is not a grid at all. In fact, it's really difficult to drive around. Just raise your hand if you've lived in a city that's not like a grid. Okay. So in a city like Boston, to get from this dot near the top down to this dot near the bottom, you can't go the direct route. Instead, you have to take this road, this road, this road, this road. In fact, they had a saying, you can't get there from here. Silliest saying in the world, but it kind of makes sense. And this new distance is an artifact of the new topology. The fact that if we are going to say there is a two-dimensional ribbon or flat piece of dough hidden in this three-dimensional space, well, then all of the distances traveled should be along that as well. For instance, if I asked you, what is the distance from red to blue on the left, then that distance should be preserved on the thing to the right. So the distance from red to blue on the left should not allow you to go across the blank space in between. You have to take the traversal within the manifold. And that's the word we often use for this structure, or this imagined surface with which, beside which the data lives. Now, once we transform it to the ribbon on the right, we only need 2 dimensions to describe each point. So we've done dimensionality reduction from 3 down to 2. And this technique you see on the left, it works in thousands of dimensions. And I've used it. It works pretty rapidly. It's kind of awesome. Okay, now remember I said that studying physics can actually help you as a computer scientist. Well, people who are working on dimensionality reduction for machine learning specifically came up with physics models, where first of all, they decided that if any 2 points are not connected on that graph, then they should push each other apart. But if they are connected, then they should pull each other closer. And maybe you only do the pushing and the pulling in a certain step. So first thing you do is you take all your points and you connect them, as we saw before. This is another view similar to this one. Just imagine it in many high dimensions. And we simply take those spheres, we expand them, so we get connections, we get a whole bunch of connections. Maybe we get it to the point where most of the points are connected to something. And then we let physics take over. We let a little bit of pushes and a little bit of pulls happen. And eventually this will settle into some kind of shape. And that shape might be a two-dimensional shape, like this shape, embedded in a higher dimensional space, or it may not. You'll find out when you do it. But physics helps with computer science. And this is one of those ways. And this is called UMAP. There's another one that's similar called T-SNE. Now, there's a lot of math behind UMAP, and there's a great video you can watch about it, and the link's at the bottom. And the guy in the video had this on one of his slides. Do any of you know what the joke on the right is? What is that a reference to? The little comment on the right is a joke. It's a callback to a couple hundred years ago. Have any of you heard of Fermat's last theorem? Raise your hand if you've never heard of Fermat's last theorem. Interesting. Oh, Justin, you have. No, you didn't raise your hand. So I thought you have. Okay, you haven't heard of Fermat's last theorem. Okay, so, oh, and you raised your hand electronically. Thank you. Anyway, we all heard of a squared plus b squared equals c squared, and there are many integer solutions to that. However, there is no integer solution to a cubed plus b cubed equals c cubed. When you do that, it's all floating points or real numbers work, but there are no integer solutions. There's also no integer solutions if you do it to the fourth or to the fifth or any number higher than 2. Fermat said that he knew this to be true, and in one of some book that he was writing, you know, the notes in the margins, in a simple little note in the margin, he says, I have a simple proof to explain this, but this margin is too small to contain it, so I'm not going to write it right now. And he never ended up writing it down. And people spent the next 200 years trying to solve it. And then finally, like 10 years ago, someone finally solved it, and they did it with a field of mathematics that some people call the Langlands program. It's a very deep and wonderful rabbit hole to go down. You should go down this sometime. Anyway, UMAP uses k nearest neighbors and some fancy math, which you can go down that rabbit hole too if you want sometimes. But UMAP is my go-to. When I have to do dimensionality reduction, my first step is always UMAP. And there's a number of implementations out there. Just use it off the shelf. There are certain things that you will maybe experiment with. Like for instance, if you do use UMAP, how big is that sphere? You know, what is the distance that you start to look out, or how many neighbors do you connect to? These are some of the parameters that you decide as you apply UMAP. But whenever I'm dealing with 1,000 dimensions or so, I start off with UMAP. Get it down to some other level. And most of the data that I deal with is not nice like this. It's not nice and organized. No, most of the data I deal with is like really messy versions of this or this. That's why I start with UMAP. So k nearest neighbors, remember, they were doing this in UMAP uses this in higher dimensions. When we study k nearest neighbors, it's just a simple machine learning model, similar things near each other, dissimilar things far from each other. So what this is saying is that when you are studying some data, things that are red are very different or most different from the things that are blue. And whatever's nearby, really nearby, like red and reddish orange, they need to be near each other in the end. And the overall distance matrix needs to be preserved. So how far exactly is lime green from red, or this specific dot from this specific dot to this specific dot? Those relative distances, they don't have to be precise exact distances in some units, but the relative distance matrix needs to be preserved as much as possible. And UMAP does that better than anything. And he uses k nearest neighbors in this high dimensions, and he uses some fancy math asterisks, as you see right there. And k nearest neighbors, just to remind you, you can set some number where you are within that k. Those are the ones you're paying attention to, or in this case, connecting to. And of course, k can change, or the size of your hypersphere can change. Now, its sibling is t-SNE, spelled like you see above. T-distributed stochastic neighbor embedding. It again preserves the relative distance matrix. Now, this one is more about preserving that distance matrix. UMAP will preserve the relative distance matrix, but it preserves it less for the sake of better finding the manifold, even if there are gaps. So if some of these dots weren't here and there's a big gap, UMAP would still work, and t-SNE might break a little. But the difference is in that fancy math. They have different fancy math. Some people like t-SNE better. I don't. I like UMAP better. And you guys can all make your own decisions as you go out there in the world, and maybe next year there'll be another new one. But t-SNE can use other sub-algorithms under the covers, and what you see in front of you are clusterings of MNIST digits. So MNIST is a popular data set that a lot of people use to train neural networks, just to play around. And the data, each single data point is actually an image, a small black and white image of a hand-drawn number. And the label is whatever number it's supposed to be. As you can see, some of the outliers that they've included at the bottom right. We have a 3, a 5, 6, 5, 2. Every one of those is just a long vector of zeros and ones. It's a 1 wherever the pixel was black, and a 0 wherever the pixel was white. And they just feed that into the system. It's maybe a few hundred pixels in there. So you have a few hundred length vector, maybe it's 700, I forget. Bringing that down to 2 dimensions gives us the images you see in front of you. When you use KNN under the covers, you get A. Then LOF, iterative, clustering, influence. The only differences really between these qualitatively is where are the outliers and how many outliers are there. But t-SNE, this is about how it does. When you do the same exact data sets and cluster it in UMAP, you get this. It's so much cleaner. It's so much better. This is just gorgeous. And every color is a different digit. This is t-SNE. Here's some more t-SNE. And t-SNE, it takes a number of steps. So when it starts off, it's crazy, like the top left. Then it starts to get better, 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 better. Epoch 3000, that's about as good as it's going to get. UMAP, I love it. I think it's cleaner. I think it's better. You can also bring it down to 2 dimensions. Okay, so we got t-SNE. Oops. Actually, this right here is a nice link you guys can all go to. And I highly suggest you do. Let's accept right here. There, that's good enough, I guess. We have some high dimensional data that was brought down to 3 dimensions. T-SNE on the left, UMAP on the right. The same exact data set. This is visual data, I believe. I just love UMAP. Just every time I've used UMAP, I felt like this is the way to go. So that's something to keep in mind. And here's just another pretty image. What this is an image of, and you can see, you can go to the link for this too. This is not clustering down to 3 dimensions. This is actually MNIST digits, I believe, but still in a number of higher dimensions. But these are 3 of the dimensions. Like this happens to be dimension number 3, this is dimension 6, and this is dimension 9. And this is another way to look at the data and think about it. You can think about, okay, let's just look at maybe the 3 dimensions that have the most variance and see what they're like. And then you can bring it down some more and try again. Oftentimes when I'm doing this kind of work, I will have many trials where I try UMAP down to a certain number, and then maybe I do some clustering. Do you guys remember all the clustering algorithms we discussed? Remember which one was my favorite? There was one that was clearly better than all the rest.
This isn't A-star, right?
No, I'm talking about
No,
clustering.
I thought it was different. Okay. A-stars.
I'm going to remind you guys by bringing up the.
Was it HDB scan?
Yes. Who said that? Mason?
Guilty. Yeah.
Good job. HDB scan. So you can bring dimensions from a very high number down to something more manageable using UMAP. And then theoretically, what you've done is you've uncurled the cinnamon roll. And then use HDB scan in that lower dimensionality, which who knows, maybe it's still a high number. Maybe it's 50, maybe it's 10, but maybe it's still some high number. Then you use HDB scan to find the clusters. And then you can bring it down further using another one. Or maybe you make the decisions differently. Maybe you bring it down to 500 and then use something and then something else. But all of these tools you've been hearing about all course long, you don't have to use just one. You can use one, then the other, then the other, then the other, all until you get to something that's within 3 dimensions. And then a human can actually understand it. And you never know what the right way to do it is. You just have to try a lot sometimes. Now, there are measured ways to say that this clustering is better than this clustering. Some of it is actually kind of hogwash. Even though it's mathematically correct, there will be ways that a human can look at something and say, you know what, even though this one was mathematically not as good, I think it's better. And the difference was there are outliers, and the computer doesn't really know which ones are outliers. I mean, it can try to guess, but it's really hard right now for a computer to really understand, okay, there is this complex shape inside there. And these over here, we can ignore them, they're outliers. All right. Before I start the next presentation, because we still got some time, I want to see if there's any questions. Nope. All right. Now let's talk about something that actually Sammy brought up. Her talk, decision trees. Okay, I want you guys all to read this decision tree. Then tell me, what is this one helping you decide?
to someone or not based on if you know their name.
Yeah, is it your ex? Are you drunk? Is it an enemy or a frenemy? Are you currently in a convertible with Brad Pitt and or Rihanna? Then yes, say hi. If not, don't say hi. Are you wearing sunglasses? Could you pretend to get a call in your cell? I think it's pretty funny. But we all have seen decision trees like this in the past. What is this decision tree trying to decide?
Whether or not to buy the car.
Yeah. Do any of you disagree with this decision tree, or does this kind of track with the way you would think if you could?
I think this has some pretty wishful thinking about someone's finances.
Yes, exactly.
Yeah, it seems also deciding you want a car based solely on the color and not the designs with the color seems a bit questionable.
Yeah. There's not enough features involved in it, is there? Are there? All right. What does this decision tree decide?
I would hope this decides whether to not give someone is this a loan?
Yeah, I think it's not getting a loan though, right? Because
Right.
you have a credit rating. If their credit rating is excellent, then it's no. So I think it's rejection for a loan.
Is it?
I'm guessing.
I don't know.
I mean, if you're a student, yes, then yes, reject them. I don't know. But this was just an example of something having to do with credit. And I thought it was interesting. We use decision trees as humans all the time, whether you think you do or not. Maybe it's so complicated you're not aware of it. But a decision tree is a way to represent knowledge and how to deal with it in the world. And it's actually really easy to learn from data. So let's say we have this data. The machine learning models that we've talked about so far, yeah, some of them could handle this, but they might struggle with it. There's no linear separation between the red and the green. There's no line we can draw that has all the red on one side and all the green on the other. So one way to handle this is to make more than one line. And decision trees are really good at doing this and learning this on their own. And we really only need 3 lines. So with these 3 lines, we can separate the green from the red really easily. What mathematical concept might we use? Let's pretend we don't want to use just gut instinct, like it looks good. What are some mathematical concepts that can help us decide where the best lines are? All right, I'm going to start calling on people from the bottom. Brennan Longstreth, what are some mathematical concepts we could use to decide where to draw the lines?
I mean, you could look at correlation between your 2 variables, I guess, within the data set. That might help you take a guess at some other concept to use.
That's a good idea. I like that. Danielle, what do you think?
Yeah, kind of going off of that idea, I was just thinking about distance, since this is a 2D representation, so something along those lines similarly.
All right, well, let's look at this same data, but in the context of a tree, because we're going to talk about decision trees. So if we decide if we're going to classify a point as red or green, we can decide based on one variable. So let's say the x here is x0, and then the vertical will be x1. So we can say if x0 is greater than or equal to -12, which is, I guess, this right here, this line denotes everything that's either less than or equal to -12 or greater. If you see there is a red dot right on the line because it's less than or equal. And that red dot being there right on the line, what does that remind you guys of? What is that similar to? What other machine learning model? There was a model that had dots that were right on the line. There's a road between them. Remember that? The road between the two halves of the data set?
Support vector machine?
Yes. So similar to a support vector machine, this dot can be used to define that line. Now for support vectors, we were defining a hyperplane. So it was better to have multiples of the dots. But here we only need one dot because we're defining a line on one feature, one dimension. So if we define every x0 that's less than or equal to -12 or greater, that creates this line that is fully designated, fully defined. Everything to the left of it is red. Everything to the right of it is green. Well, not quite, right? So we get this, we create the second one down here, x1. And we say everything to the left or equal to 9, which is this vertical line. Well, we're going to say that everything to the left of it's green and everything to the right of it is red. But remember, it's under this node. So everything that passes this node or to the left of it are things that did not satisfy that, or the things that do satisfy it, I think, go to the right. Yes. So the things that satisfy this x0 is less than -9, those go to here. And of these, just of these, the ones that are less than or equal to 9 in the x1, well, we're going to draw that third line there. So x0 negative less than that, and then for the x0 less than 9, and then whether or not the x1 divides them above or below. And those three choices tell us which of these division points you're in. So are you in the top left, top middle, top right, this one or this one or this one? And they are automatically chosen. Now, the question is, why these points? Why these positions? I mean, think about it. You right here, this goes right through this dot, this goes right through that dot, and this goes right through maybe both of these dots. I think they're both equivalent, so it goes right through both of them. So how did they even come up with these ideas? Do you think that they also tried x0 is less than or equal to -11, -9, +500? What other options did they try? How did they decide to try these specific options? What do you guys think?
Well, you could generate a series of decision trees using different combinations and then just look at which ones perform best.
Yes. Now, do you think that they tried millions, thousands, tens? How many?
In this case, probably thousands, I would guess.
So the way this decision tree was made, the way they make one decision tree is by actually trying out every point as a split point and every dimension. So right now we only have two dimensions, x0 and x1. And we have a certain number of data points. 1, 2, 3, 4, 5, 6, something like 15 or so data points. So that's 15 times 2. So first of all, we start off with x0, and we try to split the whole data set on every one of those points on the x0. Then we do the same for all the data points on x1. And what the system decided was that the number one thing to split on is x0 equal to -12. And the ones that are before it are all going to be red. Ones that are less than it. The ones that are above it, they will be the other category. Then out of the ones that are on the right hand side of that line, we're going to do the whole process again. And then after that, we'll do it again. And we'll do it again until we stop. So there has to have been a way that this system, it tried dividing x0 on this line, and it tried dividing it on this line. It could have done it here, but it did it here instead. Why did it choose this? What mathematical quality do you think it used to choose this point instead of this one, this one, this one, or even these? Throw out some words. Dominic McIsaac, do you have any ideas?
My best guess is it's normalizing rather than getting as specific as it can. It's trying to find a more general line to go around.
All right, that's a good thought. Drew Bogdan, what do you think? What's your guess?
I'm not really sure.
Well, what does this make you think of? What is that?
That looks like a logarithm equation.
What's the word for this? Does anyone know?
Heuristic?
H did stand for heuristic a few lectures ago, but this is something different. P log P. And when I say it, you guys all remember and go, oh yeah, we talked about that. Zach, what do you think? Zach Berga.
I'm not sure I remember what that equation would be.
This is entropy. P stands for the probability of something happening. So the simplest way to think of entropy is P log P. P log P. Just drill that into your brain. P log P. Now that you remember entropy is P log P, we can look at this and not get overwhelmed. Because entropy is just P log P. Remember that, simply P log P. Now, this more complicated version of the equation, X, this bigger X, these are just all your data points. So for some X in all your data, we're going to sum over that, actually all of the X's. For every one of those X's, we're going to say, what is the probability of that X occurring? And we're going to do P log P. So the probability of thing occurring times the log of the probability. And we're going to sum them up. Why is this negative sign here? Who can tell me that?
Is it because well, at least with in chemistry and biology stuff, when entropy is kind of going in a, I don't know, you're losing stuff, right? Kind of.
That's a good thought. And I like that you brought up chemistry, because entropy does come from chemistry originally. So probabilities are always between what and what?
0 and 1.
Yeah. What is the log of a number between 0 and 1? Is it positive or negative? Anyone know? Like the log of 0.5. Is that going to be positive or negative?
It's negative, right?
Negative.
Negative. So that's why we have this negative sign out here. We want the entropy to be a positive value. So to make it a positive value, it's negative all of this. Now, the question came to my mind when I first learned about entropy. Why do it this way? Why not just have some easier, simpler equation and then we'll call that entropy? Well, it's because of the beautiful things that this enables. So let's just presume we kind of understand it, soak it up, say, okay, P log P, entropy is P log P. And we're going to say this is a useful concept and then we'll see how we can use it. Now, here's another way to write it. Why does this one not have a negative sign? It's still correct. Here's the first one again. Now here's another version. Why does this one not have a negative sign?
Well, you're dividing 1 by the probability, so you're gonna get
Yeah.
a number larger than 1.
Yes, exactly. So there's this fun thing with logarithm where yeah, if I want, I can take this P sub I and move it up and make it in the numerator, and then it becomes negative. So again, it's just another way to write P log P. Just remember that, P log P. Okay, here is a decision tree. Does anybody recognize the data set this is from? Some of you have actually used this data set in your homework. Come on, guys.
Is it the IRS data set?
Yes, the IRS data set. Very good. So somebody used the decision tree to classify the IRS data set. IRS data set has a few different dimensions, x0, x1, x2. Some of them are petal width. Another one is sepal length. So let's say they did exactly what we saw with these other points, where they went to they first of all went through x0 and looked at dividing it based on every x0 in the data, which again, as you can do it, it's only 15 tries. And then they did for the x1s. Well, they did this for the IRIS data set. And after they did that, they figured out that the best first split is on petal width. So for the moment, ignore all other dimensions and features. And just on petal width, things that are less than or equal to 0.8, they're one class. They're going to go to the left. And everything else goes to the right. Now, here's where the entropy helps us make this decision. The original entropy before you make the split is 1.585. What that means is that if you compute this equation for every data point before you split it, you get 1.585. After you split it, you get two sets. You get, things on the left of some line and things on the right of some line. So now, separately for each of these two classes, we're going to compute the entropy. The one on the left has an entropy of 0. How on earth do you get an entropy of 0? Well, let's look at this example. On the tree on the right here, this tree, which node do you think might have an entropy of 0? Which nodes plural?
The
Entropy.
leaves.
Yes, those leaves, but they're not the only ones. There's actually they are. This is also a leaf. That's right. Anything that is pure. Now it's possible that you end up with a leaf that's not pure and you decide you don't want to split it because maybe it doesn't help. But anything that's all one class, all red or all green. Here we have another all red and an all red. Those have entropy of 0. So when they split on petal width, all of whatever went this way, they all had the same class, same class of iris. So the entropy was 0. Now the ones on the right, they still had some entropy. Now this splitting on petal width, we have entropy before and we have entropy after. What do you think we were trying to do? Like, how do we know this split? If we're just looking at entropy, why is this split the best? So Claire, why don't you look at those two, add up their entropy. What does it equal?
1.
What was it before?
1.585. But what I'm
Yeah.
noticing is that it split the values perfectly. Like the first one is perfectly divided from the second two.
Well, what we're saying is that before this first one, we had all of the data in one giant clump. And then we say, you know what? For some of them, the ones with petal width of less than 0.8 go one way, and the other ones go this way. Now, before we did the split, we calculated entropy, it was 1.5. After the split, we have a total entropy now of 1, 0 plus 1. That's what this is saying.
Minimizing total entropy then?
Yes. And what you don't see here is all of the other splits. All of the other choices they could have made, like if deciding to do the petal width on 0.7 or 0.6, none of those were as good as this one. This one had the lowest total entropy. Another word for the amount of entropy difference between here and above is information gain, because information is the opposite of entropy. How much information, how much entropy. They're two sides of the same coin. More information means less entropy. So making this split was the best of all possible splits. Then again, from here, right in this one little square, we've got an total entropy of 1. When we split it, we get a total entropy of 0.445 plus 0.151. That is a good split. That split gives us a lower total entropy than the set from which it came. So we are applying the same idea recursively to every node in this tree. And we keep doing that. Now we get down here, the entropy for this little cluster right here, it's 0.65, it's not 0. Here, this one was 0. So obviously, if you have a cluster that's perfectly pure, you don't split it, there's no point. But why is this one not split? It has an entropy of 0.65, it's not 0. Why isn't that one split? Lynn I, do you have any ideas?
Maybe because there's only like one left on the second label, and like no matter what they split, like it doesn't lower the entropy. Like
That's
there's
it.
no way
Yeah.
way to make it pure. Yeah,
That's
and it's only one
exactly
left.
it. Well, it's not that there's one left. There could be many left, because if there was only one left, then the entropy would be 0. It would be pure. But we see the entropy is 0.65, so it's not pure, but you actually had the right answer in what you said. It did not make it better. They tried all the possible splits, and none of them had information gain. All right. Does that make sense, everybody? All right, so now you know decision trees. Isn't that nice? Now, what's nice is everything is at a depth of log 2 of n. So you could have n things in your tree, and to find something on average, it's going to take, log 2 of n to find it. That's how deep on average these trees will be. That's much better than n or n squared. So decision trees can operate very fast. Now, these are just 2 other examples of trees. You guys have all heard of a random forest. We mentioned them in class. A random forest is a bunch of decision trees. But the weird thing is, we just talked about decision trees, how to make them, and you start off with the data. You choose the best split, and you do that first. Then the second best split, and you do that second. Then the third best split. There's no ambiguity. There's no randomness. So why a random forest if there's no randomness? Does anybody have any guesses? We are at the end of class, so I will just tell you the answer and you guys can go your merry way. So you randomly select from the data with replacement. That means when you're selecting all your data points, maybe you'll get that first one, that first data point 5 times, and you won't get the second one, you won't get the third, and then you get this one twice. So you randomly select data from your data. Then you randomly throw away some features, just use some of the features, and you make a tree. Then you do it again and again. Sometimes I will make 10,000 trees on the same data. And then those trees vote. Now you know random forests. Any questions before we say good night? All right, thank you, everybody. Good luck on the NIM competition.
Have a nice night.
Thank you.
Thank you.
Thank you.
Thank you.
I have a quick question.
Yeah.
Is entropy, like in like the hard sciences, is a state of disorder, like or measurement of state of disorder? Then like when we say that it's like information gain, does that mean that like I forget, do we gain more with like a lower entropy we gain more information? Is that
Yeah.
right?
Do you remember one of the things I had someone do in class very early on? I had them sit, I think it was Michael, I had him come
Oh,
up.
the pens. Yeah,
Yes.
okay, that makes sense. Okay.
Yeah.
Got it. Thank
So
you.
in the low entropy state, when he touched the pen, he had information on the other pens.
Right. Okay.
Yeah.
Gotcha. Thanks.
Mike,
Sir.
that was you, right?
Yeah, that was me. Can you hear me, sir?
Yes.
Okay.
Okay.
For the NIM competition, we're allowed to hard code values into our program, right?
Yes, you can do whatever you want.
All right. Thank you.
Is that all?
Night, sir. Yeah, that was all I wanted to ask.
Go for it, man.
All right. Thanks. Bye.